All right, so this video is going to cover how we calculate and do problems in conservation of angular momentum. So we have a video on the conceptual ideas of the conservation of angular momentum. Now we're going to use those ideas and apply them to a problem. And we're going to go through the process in which we solve these types of problems. And I think you're going to find that it's pretty similar to the process that we solve linear momentum conservation problems. Rightfully so. So let's get at it. An example problem of conservation of angular momentum. So let's imagine you and your friends are at a playground. And at that playground, they have one of those merry-go-rounds that there's basically a rotating platform that you stand on. You kind of hold on to the handle at the end. And as you're going around on this merry-go-round, you know that if it goes too fast, you can't hold on while standing at the end. So you're going to play a trick on one of your friends. You're all going to start out. So here's a top-down kind of view of the merry-go-round. You're all going to kind of start out, hanging out, rolling around that merry-go-round on the end. And at a certain point, you're going to cue 3 of your friends to all go towards the middle really fast. The idea being whoever's left out at the end is going to go flying off. All right, that's what you want to do. Now, you know that if you are rotating at the edge of that merry-go-round and your angular speed is over 5 radians per second, you cannot hang on, right? So what conditions, or the condition I'm going to give you, is it enough to do this trick to your friends so that if you're rotating at a certain cue point, you all jump to the center? Is the merry-go-round going to reach the critical angular velocity for your friend to not be able to hold on and go flying off? And you all get a good laugh. All right. Of course, we do need to know a few ideas about the merry-go-round. So, first idea, we know that the diameter of that merry-go-round is 3 meters. Okay, so it has a diameter of 3 meters, and that merry-go-round has a moment of inertia of 130 kilograms times meters squared. Now this is a flat, relatively uniform disc, but it has these like handles on it. So I'll just give you that the moment of inertia of the merry-go-round is 130 kilograms. We are going to kind of group everybody into one size and mass, and we're going to say that the mass of the person, of any one person, is equal to 60 kilograms. Okay, so the size of the person, I just want to double check my thing, just to be, 60 kilograms, make sure I'm consistent. So each person has a mass of 60 kilograms. The diameter of the merry-go-round is 3 meters, and it has a moment of inertia of 130. Now the last piece of information we need to know is that when you go towards the center, so when you're out on the edge, you're at a radius of 1.5, that's the diameter, so you're at a radius of 1.5 meters, but you're all going to jump to the edge, and the closest you can get to that axis of rotation is 30 centimeters. So you move to 0.30 meters away from the center. All right, so hopefully that kind of picture makes sense. So if we look at, if this is our initial condition, and just like with linear momentum, we want to define the initial and final. That's our initial condition. I'll use a different color. Our final condition, here's the center. And now 4 of you are close to that center, 0.3 meters away from that center. And then there's the buddy, you're kind of playing the trick out. That's still 1.5 meters away from the center. All right. So that's our scenario. I think I have all the important pieces. Oh, we need one more piece. The last piece we need to know is that the Q is when you reach an angular speed of 2 revolutions, not an angular speed, excuse me. When you're rotating at 2.0 rotations per minute. And again, not 2.020. Gotta make sure my numbers are right from my notes. So 20, and I'll use two significant figures. So 20 rotations per minute. So I'm gonna just make sure that also has two significant figures. All right. Is this the right time to mark that cue? Is this gonna work in our trick on our friend? So we're gonna use linear angular momentum to solve this problem. Want to keep in mind a couple of things. Remember, our angular momentum is equal to our moment of inertia times our angular velocity. So that's going to be important for us. And just like with linear momentum, when we look at conservation, we have to understand what is the system. So we know that the initial momentum of the system is going to equal the final momentum of the system. And that's really, really important. It's always of the system. So we have to define our system. We have to make sure we know what pieces are part of that system. So let's do that first. We're going to define our system. We know that the merry-go-round is rotating. We want to think of what all is rotating. The merry-go-round is rotating. So the merry-go-round, I'm just going to say MGM, that's part of our system. And of course, each individual person, the people, are part of our system. All right. So those are all the pieces that make up both the initial condition and the final condition. So we have 5 people in our system, right? We have all the friends in the system, and then we have the merry-go-round itself. So our initial system consists of the initial for person 1, the initial for person 2, the initial for person 3, the initial for person 4, the initial for person 5, and the initial for the merry-go-round. Okay, I don't know why I'm calling it MGM. It's a merry-go-round. It should be MGR. Let's change that, MGR. All right. That is our full system. So all of these pieces make up the system. Similarly, we have, I'm going to swap colors so I have a little finer tuned marker. We have the system in the final. We have the final momentum of person 1, the final momentum of person 2, final momentum of person 3, final momentum of person 4, final momentum of person 5, and the final momentum of the merry-go-round. I have enough space. Perfect. I'll kind of give a little break there. So all of these pieces make up our final system. Now, can we do a little combining here? We have each person with the same mass. We have each person at the same location. So a mass moving in, rotating at a location has the same moment of inertia. And since they're on the same turntable, they have the same angular momentum. So in my initial condition, all 5 of these objects, all 5 of these people, L1 person, L initial person 1, equals L initial person 2, equals L initial person 3, and so on. They're all the same. So we actually have 5 identical, 5 initial momentum of the people. All right? They're all the same. The same radius, the same mass, the same angular velocity. Okay? So the merry-go-round has a slightly different angular momentum because it's got a different mass distribution, but it is going the same velocity, angular velocity. So this really reduces our initial condition. What about our final condition? Is the same true on the other side? Well, on the other side, 4 of my people are all in the same situation, same mass, same radius, same angular velocity. They're all still have the same angular velocity. But 1 of my people isn't. So in my final condition, I can combine 4 of them, So I know that L final of person 1 equals L final of person 2 equals L final of person 3 equals L final of person 4. So I have 4 L final of person, and I'm going to designate this one, person 1, plus I have my final angular momentum of person 5, plus I have the angular momentum of the merry-go-round. So slightly different on the end side because the people are in a different situation. They're in a different location. All right, so we've kind of simplified our system a little bit. And now we can explore what those angular momentums look like. All right, well, we know that the angular momentum is equal to the moment of inertia times the angular velocity. So in the case of my people, I have 5 times the moment of inertia of people times the initial angular speed of the system. They're, in this case, they're together. So we know that the angular speed of the merry-go-round is the same as the angular speed of the people, plus my moment of inertia for the merry-go-round times the initial angular speed. Similarly, in the final condition, we have 4 times the moment of inertia, I'm going to say of P1, times the final angular speed, plus the moment of inertia of P5 times the final angular speed, plus the moment of inertia of the merry-go-round times the final angular momentum of the system. All right, so now I can pull out my angular my angular speeds, and I have the initial angular speed times 5 times the moment of inertia of a person plus the moment of inertia of the merry-go-round. And this should make sense. Our moment of inertias of the system are going to add together. That's going to equal our final angular momentum times 4 times the moment of inertia of person 1 in the middle there, plus the moment of inertia of person 5, plus the moment of inertia of the merry-go-round. So I just did a little algebra, pulled out my angular speeds. All right, so how do I find the moment of inertia of a person in the initial condition? We want to keep in mind that we consider these point masses. And so I'm looking for a space to write it. The moment of inertia of a point mass about an axis is the mass times the radius squared, where that r is to the axis of rotation. So following through with that process, we have the initial angular speed times 5 times the mass of each person times the radius in the initial condition. So let's call the initial, we're going to say radius initial squared plus the moment of inertia of the merry-go-round. That has to equal our final angular speed, 4 times the mass times the final radius squared, plus, now I have a different moment of inertia for person 5. They have the same mass, but they're at that original radius. They're still on the edge. So we can say times R1 squared, or initial squared, plus, of course, the moment of inertia of the merry-go-round. And now we have a whole bunch of numbers we can just plug in. Everything now is known, and we're going to then solve for our final angular speed. So we have our initial angular speed, which was, it's given in 20 rotations per minute. Do I have enough? I don't think I have enough room down there. So I'm going to kind of scoot this up top. I have a little more space. We know that 20 rotations per minute We need our angular speeds in radians per second. That's what I asked. We don't need them in radians per second, but we're assessing, is this situation going to be enough to get us to that 5 radians per second mode? So we got to figure out what our initial angular speed is in radians per second. So we have 20 rotations per minute. We know in 1 minute there are 60 seconds. It's going to let me get rid of that minute. And we know that there are 2 pi radians in 1 rotation. So that's 40, 20 times 2 times pi. That's going to be 40 times pi. And we have 125.6. Something is not right here. Oh, divided by 60. I'm like, that doesn't make sense. Divided by 60. Oof, that wasn't working out. 2.09. Well, that's where my 2 came from. This is equal to 2.094. We're going to keep some units there because we don't want to round too early. Radians per second. All right, so that's my initial speed. I forgot to do that divided by 60. So we have 2.094 times 5 times 60 times 1.5 squared plus 130. That is going to equal our final 4 times 60. What's our final radius? 0.3 times 0.3 squared plus 60 times the original radius, because that guy's out there, times 1.5 squared plus my 130 for the merry-go-round. I'm getting really tight to the end. So as I get really tight to the end, I guess I should just do it. So we all do it together. So we have 5 times 60 times 1.5 squared plus 130 is 805. So this is 805, and I'm just gonna, I don't want you to think I'm dividing. This is all 805. So we have, just don't want to run out of room. We have 2.094 times 805. That equals, I think we're still okay on space, W final times, let's see what this one is. So we have 4 times 60 times 0.3 squared. This is 21.6 plus 60 times 1.5 squared, 135 plus 130. So that equals W final times 130 plus 135 plus 21.6. Probably could do that in our head. 286.6. And now I am totally out of room. So let's see. We're going to solve for V final, omega final, excuse me. And I'm going to erase this up here. Oops. Slight time delay. You've probably already calculated it on your own. I'm just going to rewrite what we have over here. So did we do that? We did not do this yet. So we have 2.094 times 805. 1/6. So I'm going to just move all of this up. Okay, so we have 1685.6 2.67 equals W final, omega final, sorry, not W, times 286.6. So our final speed when we all jump to the center is 1685.67 divided by 286.6, 5.88, but I'm rounding now to my two significant figures, radians per second, which is well over that 5 radians per second. So indeed, our buddy goes flying off as soon as we jump to the center. All right, long problem, a lot of words. Let's just do a quick recap. Recognizing a couple of things. One, it's the system we have to pay attention to. So we understand that momentum is conserved in a system. We must define that system. All of the objects experiencing that rotation in that sort of collective manner. The system the items in the system did not change, and they can't as we go from the initial to the final. But they looked a little different, right? The angular momentums of each individual item may have changed, and in this case, they did. As they always, not always, but as they often will, they certainly will change when the angular velocity changes. And so the angular momentum of the individual elements changes, but the angular momentum of the system does not change. That's what's important. So now we use that information to recognize what pieces are collective. So this particular line here, this is the one that really shows the understanding of the physics, right? We know every momentum in the system, of each object in the system, every one of each object in the system. And then we started to recognize that some of these things are similar. These 5 all have the same, so we collected them together. These 4 all had the same, so we collected them together, and we did that manipulation. All right, recognizing, does it make sense conceptually? Should we have sped up as we moved more mass to the center? Yeah, because overall the moment of inertia went down. You can see that in this last step here. The moment of inertia of the system was 805. It went down to 286. That is that idea that as I bring mass closer to the center, I decrease its moment of inertia, and of course then the angular momentum goes up. All right, good job.